Okay, so a particular class of linear second-order differential equations with constant coefficients. Now, these particular equations are reasonably straightforward to solve, but we need to actually look at the system of solution. But in essence, the solution of such an equation y can be thought of as broken up into two parts, into ycf, which we call the complementary function, okay, and ypi, which we call the particular integral. So this is called the complementary function. Okay, it's called the complementary function, and this is called the particular integral. Basically, the idea is as follows. The YCF is in fact the solution to the equivalent equation where this is in fact the solution to the homogeneous equation, the homogeneous version. Every second-order ordinary differential equation can be written as a homogeneous equation by simply letting the right-hand side be 0. So the solution to this differential equation that you see here, which is the homogeneous version of this equation, all I've done is I've set fx to 0, okay, gives me the solution to this homogeneous differential equation is called the complementary function. So what we have, and the other part, the pi, this one here, the particular integral, relates to when we bring this back into the problem. So the idea is this particular method is based on a similarity solution idea, which means that we assume a solution that the equation that will satisfy the equation, we substitute it in, and then we try to fit the coefficients and so on. So the first thing we're going to look at is how do we solve, or how do we find this complementary function? So that's going to be our first aim, and then we will turn to the particular integral a little later. Now, if we let, through experience, we let's say YCF equal e to the lambda x. Now, if I substitute that into the homogeneous equation that you see here, this one, what I end up with is, in fact, a lambda squared plus b lambda plus c, okay, into e to the lambda x equals 0. That's what I end up with. Now, I know that e to the lambda x can never be 0 because that will require x to be negative infinity. Now, so therefore, the only way this equation will be satisfied if a lambda squared plus b lambda plus c were 0, in fact. Now, if I can find these ABCs, I'm sorry, if I can find this lambda, then that, in fact, y equals e to the lambda x is the solution to my differential equation. So here, it boils down to really looking for the complementary function by looking at the solutions to this quadratic equation. Now, of course, we have quite a bit of knowledge about quadratic equations. We know about quadratics that there can be 3 possible scenarios. So, for instance, if we look at this quadratic equation, this can have it can have 2 distinct real roots. Okay, so 2 distinct real roots. Okay, it can have a double root, okay, which means a repeated root. And third and final possibility is that it can have complex roots. So what we'll do is we'll have a look at, in fact, in these 3 cases, what different solutions do we end up with for the complementary function. So here you can see the solution to this equation from the quadratic formula is minus b plus minus square root of b squared minus 4ac over 2a, and it's this b squared minus 4ac that is key to the different roots that you get. If it's equal to 0, you get a double root, okay, and the double root in fact turns out to be minus b over 2a. So lambda is equal to minus b over 2a. And it's a quadratic, so it should get 2 roots, so it's called a double root. The other one is, of course, if b squared minus 4ac is greater than 0. Greater than 0 will give you distinct roots, okay, so then lambda is equal to 2 possible distinct real roots. And the third case is if b squared minus 4ac is less than 0. And if it's less than 0, that's when you end up with complex roots. So if we look at the case where we get two distinct roots, so that means that when b squared minus 4ac is greater than 0, let's say we let the two roots be lambda equals alpha and lambda equals beta. So, and here of course alpha is not equal to beta. So there are two distinct roots. In this case, what happens is when we substitute this into the solution, so we end up with two solutions. Y is equal to e to the alpha x, and y is a complementary function, of course, and also it's equal to e to the beta x. Now, we know that these for homogeneous equations, both these in fact are solutions. So the combined solution, the complementary function, is some constant e to the alpha x plus some arbitrary constant e to the beta x. So this is our complementary function in case we have two distinct real roots. Because the solutions are linearly independent of each other, the sum of these is also a solution. Okay? So in fact, they form a basis for the space of solutions. Anyway, in case you don't understand that, basically what it's saying is that if you have two solutions like these two exponentials, then a linear combination of them is also a solution to the same differential equation. It's very easily proved. You just have to substitute it into the homogeneous equation, and of course it will satisfy the equation. Next is the case of the double root. So this is the case, let's say here, this is case 1. We have distinct roots. Case 2 is b squared minus 4ac is equal to 0, which is a double root, which means that lambda is equal to, let's say for the sake of argument, let's call it gamma. So lambda is some constant gamma, which actually we know it's in fact minus b over 2a, but let's use it just for simplicity's sake. In this case, the complementary function is in fact a plus bx into the exponential of gamma x. Okay. Now, of course, this is not obvious. Clearly, what we're saying is there are two possible solutions here, because we need two solutions, essentially. So here, the other solution is bx gamma x. So you will see that individually, both of these are solutions to the differential equation. Now, that can be easily proven. All you have to do is to take this and put it back into the original differential equation. But if you were to substitute it, in theory, we know that ae gamma x satisfies the equation. What is not intuitively obvious is bx e to the gamma x also a solution to the differential equation? Well, you can easily check that. For instance, if ycf dash is going to be, and let's check it for the second one. Leave the first one because it might be obvious. But if we look at the second one, what happens is you get b e to the gamma x plus gamma b x e to the gamma x. Okay, and the second derivative of this is essentially gamma b. Okay, gamma b e to the gamma x plus you have a gamma b here and e to the gamma x. All right, plus you have the gamma b still there, and in fact a gamma squared rather, b x e to the gamma x. Now, if you put these all together, in fact, into the differential equation, the original differential equation is, which I seem to have rubbed out here, but anyway, it's a y double dash, so it's a times gamma b e to the gamma x plus gamma b e to the gamma x plus gamma squared b x e to the gamma x plus b times the first derivative, which is b e gamma x plus gamma b x e to the gamma x, okay, plus c times bx gamma x is equal to 0. Okay, so you can combine these and you end up with this. Now, at this point, we need to think carefully about this. Now you see, remember what is gamma? Gamma is minus b over 2a. Okay, it's minus b over 2a. Now, if gamma is minus b over 2a, now there's two ways to think about this. Now, we already know that gamma is a solution to this quadratic anyway. So this, we know that a gamma squared plus b gamma plus c is equal to 0. Okay, so this whole thing goes to 0. Now, that leaves us with this. If you substitute minus b over 2a into this equation, you'll get 2a into minus b over 2a plus b, which is equal to 0. So therefore, this is a solution to the equation. In case you're confused or still don't believe it, keep in mind that you can replace, remember, b squared is equal to 4ac in this situation. So c is equal to b squared over 4a. If you really are not convinced, you can actually substitute that in. Bottom line is, this is a solution, so it does satisfy. Just for your curiosity, you won't find this in a lot of texts. People have ignored this and just use the solution x e to the gamma x as being the solution. So this is you can skip over this. If you find it too confusing, just skip over it. But anyway, the bottom line is that your solution, our solution, the complementary function as said above, is a plus bx into e to the gamma x, where gamma is that double root. Let's move on. So the third case is b squared minus 4ac is less than 0, and we assume here then that lambda is equal to u plus minus iv, which is complex roots. Our complementary function ycf in this case happens to be e to the ux into a cosine vx plus b sine vx. All right, and those are the roots. So here, let me just summarize this for you very quickly. So here's a summary. If your real distinct roots, your complementary function is the ae alpha x plus be beta x. If you have real double root, and the double root happens to be gamma, then ycf is equal to a plus bx e to the alpha x, gamma x, and the complex roots u plus minus iv, then your complementary function is the exponential ux times a cosine vx plus b sine vx. So that basically, this is the important result. This helps you calculate basically what your complementary function is. Okay, and we'll look at some examples in the next video.